a quick recap of what we were doing in the last class. And what we said was, we are already familiar with solving for the network when the network is linear and time invariant, and what we do is basically write the M&A equations, and in this simple case you would have basically, I want to write the whole thing down without, so that's G plus J 2 pi F C minus G, and we have this is 0 and V2, that's basically this guy here. So that's V1, V2, capital IS, right? That basically equals zeros, right? And the moment we made the conductance time varying, if this was G of t, then the process remains pretty much the same, except that what's the difference now? Basically we replace, so the unknowns now become column vectors, right? And so V1, V2, IS, etc. are 2 capital K plus 1 cross 1 matrices, right? And G F, etc. become 2K plus 1 cross 2K plus 1 matrices, and the zeros and ones on the left and right hand side are, you know, square or column vectors of appropriate order. And so all that we need to do in the M&A formulation is to basically replace each of these guys with the appropriate matrices, right? Okay, and so all these are now matrices. When I write this of course is what it means is that we have K zeros, 1, another K zeros, right? And while this might be difficult to solve by hand, it is definitely pretty straightforward to go and solve by computer, and in one shot, just like how we get all the transfer functions that there are corresponding to all the branch voltages and the currents in the voltage sources. Now when you solve these, in this particular example, as you can see, there are 2K plus 1 times 3 unknowns, right? So they correspond to not only the voltages, node voltages V1 and V2, they also correspond to and the unknown current. So I mean the current in the source voltage source, but more importantly, with each unknown you're actually getting all the harmonic transfer functions in one shot, right? So while it is true that you're doing a lot more work, which is inevitable because the conductance is varying with time, it's also true that you're able to get all those harmonic transfer functions in one shot. Now, as you keep changing the input frequency, you have to basically solve these this set of equations for every frequency point out there, and therefore get the frequency response. Okay. Now, I think it's high time we did an example. So, again, let's do something that we should be able to understand the result. So, let's assume that this conductance is varying periodically from the conductance is 0 for half the time period, right, and is since C is 1 farad, Ts is 1 second, and the conductance is some very large number. Let's call that G max, and G max happens to be some very large number. Okay. So, for all practical purposes, therefore, how does this this is equivalent to? It's basically not strictly a sample and hold. It's what is called a track and hold, because during this period, when the switch, when the conductance is very large, when I say very large, remember that the conductance is say 10,000 and C is 1. So, the RC time constant is C by G, which is 10 power minus 4 seconds, right. And as you can see, that is very, very small compared to half the clock period, and therefore, the output voltage will track when the conductance is large. The output voltage will pretty much track the input sinusoid almost instantly, right. And when G is 0, what do you expect? Well, the conductance is 0, so it's an open switch. So, this is an example of what is called a track and hold circuit. Okay. All right. And sometimes the RF guys call this a sampling mixer. Right, for obvious reasons, right. And the effective sampling instant is the moment the conductance goes from a high value to a low value. So, as usual, I mean, you can write the M&A stamps of all this and set up a bunch of equations. It will be this set of equations where that G is basically what do you call, we already saw that the conductance matrix G is nothing but, what will it be now? This will be, what will be the first term? It's within quotes the DC value of the conductance, and it will be G max by 2, right, or let me just call this G sub 0, right. So, G of t, as you recall, is sum over k, G sub k e to the j 2 pi Fs, k Fs, Fs is 1, so k times t, all right. And so, what is the, so this is G 0, and this must be G minus 1 all the way up to G minus 2k. All right, and this must be G1 blah 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 G2k, and all this will be, so this is G0 and this will be G0. All right, you plop it into MATLAB, you can go and solve, and of course we're not going to do it here. It turns out I already did the math. Okay, and okay, it really doesn't matter. I used a G max of 2 pi into 1000. It really doesn't matter whether it's 1000 or 10,000. Pretty much it's the same thing, right? Okay, so first things first. So I assumed 1000 harmonics. So K was assumed, the capital K was assumed to be 1000, right? So how many equations do we have? We have 2001 multiplied by 3, some 6000 matrix of 6000 by 6000 approximately, and you invert it, right? Basically then you can plot the magnitude and phase of all the harmonic transfer functions, right? And this is what turns out, this is what we get. Okay, now let's try and see if run some sanity checks and see if we can understand any of these, at least mark the special points, and then make sure that these things make absolute sense, right? I mean, see, you plop something into MATLAB and you solve an equation, you put in garbage, you'll get garbage out, and you can plot pictures, right? But you also want to make sure that what you plot makes sense, right? Okay, the easiest point to check for is, pardon? DC. All right. So for DC, what should you expect for H0 of 0? What does it mean? What does H0 of 0 mean? So you apply, what do you apply and what do you measure? We apply a 1 volt DC, right? And you get some waveform here, correct? And what should you measure in that waveform? The DC component of that waveform, right? So if you put in DC here and this resistor is changing periodically, what comment can you make about this waveform? Pardon? It will be constant, right? Because if it's constant, there's no current flowing through here. If there's no current flowing through here, there's no voltage drop across the resistance. So basically, one way or the other, you've solved within quotes Kirchhoff's voltage law and current law, right? It's a hunch, right? Technically speaking, you have to go and solve, you have to go and plop in that, put f equal to 0 in that set of equations and then go and solve it. But in this case with DC, it is straightforward enough that we know what to do. So if you put in 1 volt DC, the output is going to be simply a DC of 1 volt. So what comment can you make about H0 of 0? It should be 1. Does it make sense? Right? So that's something that fortunately works out when you solve the equations also, that confirms our intuition, right? Okay. Now the next question is, what about H minus 1 of 0? What should you expect? What does this quantify? What should be the input and what should be the output that we are looking for? We want to put in, you want to put in DC, and what are you looking for at the output? You're trying to find what the strength of the output is at a frequency? Fs or minus Fs? See, this is the input, I mean, Hk of J2 pi f, right? So this is the input frequency, and what is the output frequency? f plus k times fs. All right. So h minus 1 of 0 basically means that the input frequency is DC, the output frequency is, so input is DC, output is 0 minus fs, which is minus fs, right. In this case fs is 1 hertz, so basically you are looking for an output, the component of the output at minus 1 hertz. And well, it does not require a genius to figure this out. The output is a pure DC. So, if you Fourier decompose the output, what do you get? Well, you only get DC, all the other components are 0, and therefore, h minus k or h sub k of 0 for k h sub k of DC for k not equal to 0 must all be equal to 0. Does it make sense? Right? And again, sure enough, you plot the magnitude of h minus 1, h plus 1, h minus 2, whatever, right? All of them turn out to be 0. Right? Another thing, what did we realize about this conjugate symmetry conditions for these harmonic transfer functions? So h of hk of j2 pi f must be equal to h minus k star of minus j2 pi f. Correct? So and hk j2 pi f is not necessarily equal to hk of engine, right. So that basically means that as you can see here, we've computed something. We'd like to see if this makes sense. So h1 of f is not the same as the magnitude of h1 of f is not the same as the magnitude of h1 of minus f, right. But for h0, well, if you put h0, then k and the negative of 0 turns out to be 0 itself. So apart from h0, all the others will not necessarily obey, will not have a magnitude response that is even, right. Okay. So as you can see here, yeah, sure enough, h1 is not symmetric about the magnitude is not symmetric about the origin, right. However, h minus 1 of j2 pi f in the for positive f is the same as h plus 1 for negative frequencies, correct. And similarly, h minus 1 for negative frequencies should be, we expect it to be the same as h plus 1 for positive frequencies, and that's indeed true. All right. So well, that seems at least reasonable. I mean, this is what we expected. I mean, no big surprises there, right. Now let's try and calculate some other salient points, and perhaps we calculate let's see, h1, h plus minus 1 of j2 pi f for f equal to 1, right. How do you do this? What do you suggest we do? Well, h0 of 0 must be 1, h sub k of 0 must be 0 for k not equal to 0,